All right, so let's proceed ahead. And our next topic is skewness and kurtosis. Although in yesterday class I did told something about it. Okay, when we were discussing about the imputation. Okay, so while analyzing the data, doing exploratory data analysis, skewness and kurtosis is very much important. Okay, that means especially during data visualization. Fine. So, skewness measures the degree of asymmetry in the distribution, and kurtosis measure the degree of peakness or flatness in the distribution. Okay, and as I told that data distribution is everything here, and we want to understand data distribution only. That's the science. All right. So it's saying that skewness measure degree of asymmetry in the data. That means either you are left oriented or right oriented. That is asymmetry. Flatness means how long the tail is. Okay. Flatness, peak. That's what it shows. I will show the diagram also. That's what it means. Okay. Let's have some differences to be checked. So skewness, degree of asymmetry. Kurtosis, peakness. Okay, how much flat your peak is? Like, okay, I think it should be like this. Here it is. Okay, so this is your kurtosis. Okay, this is your kurtosis. Okay, like when this. Okay, so like if you represent data in such kind of distribution, and if you represent data in this kind of distribution, you can see that this is more flat and this is sharp. Okay, so this is flat, this is sharp. So in case of kurtosis, it's referring to this point only, degree of peakness of the distribution, or I can say degree of flatness of the distribution. That's what is represented by the kurtosis. Okay, then it is having the range of values minus infinity to plus infinity. It is also having the same thing, minus infinity to the plus infinity. It is called as the third moment of distribution. It is the fourth moment of distribution. So we are having a data distribution. So this is third moment of distribution, and this is fourth moment of distribution. Okay, not so much important that thing, but here is the interpretation. We can have negative skewness, zero skewness, and positive skewness. Negative means we are having much more alignment on the left hand side. Left skewed is negative skewed. Zero skewness means there is symmetry. Positive skewness means we are having much more alignment on the right hand side. So left skewed, the distribution is more on the left hand side than it is negative skewed. If the distribution is more on the positive side, then it is like right. Okay, right skewed, positively skewed. Okay, and in case of kurtosis, we are having three different types: platykurtic, zero, and leptokurtic. Platykurtic means we are having a flat peak. Okay, as I told right now, this is the flat peak. Flat. This is flat. Okay, so this flatness is represented by platykurtic. Platykurtic. Okay, zero kurtosis means normal, just like normal distribution. And leptokurtic means sharp. I also shown you the sharp thing. So this is leptokurtic. Okay, fine. Skewness affects the distribution, center of the distribution. It affects the center of the distribution. Okay, because if there is asymmetry, the center of the distribution will be different. Okay, and it put large impact on the mean than the median. Okay, however, in In case of kurtosis, it affects the tail of the distribution. Okay, high kurtosis has more extreme values and it can lead to large standard errors, more extreme values. Okay, so higher the kurtosis, much more flatness will be there, so extreme values will also going to be more. Okay, fine. And these distributions are used in where you do have a numerical continuous feature. Okay, fine. So let me again, now let me reshare my screen and talk more about it because these are important concepts. Okay, so I'm sharing my entire screen. Okay, fine. Now listen carefully. So right now we are dealing with data distribution, and especially we are having numerical data, numerical which is continuous in nature. Okay, which is continuous in nature. And because of this continuous distribution only, we can make histogram for it, histogram or distribution plot for it. And while interpreting the distribution, we found that there are two things. One is skewness, another is kurtosis. Okay, so if I do make again this thing, it's a normal distribution. If there is a symmetry, this is my reference plot. This is normal distribution. Symmetry. This is bell shape. However, skewness means deviation. Okay, skewness means your right or left deviation. Okay, so if I make like this, that means your much of the data is aligned on the left hand side. Left, left skew. This is left skewed. And if I make like this, okay, it is right skewed. That means your most of the data is present on the right. This is right skewed. Okay, so left skewed, what I am saying here, according to your definition, on left hand side, okay, it indicates a long tail on the left hand side. Long tail on the left hand side. Okay, now check. Is there where is a long tail on the left hand side? Here it is having a long tail on the left hand side. Long tail on the left hand side. But I am writing here it is right skewed. Just like now understanding it according to our convenience. Skewed means okay, I am referring that okay, most of the data distribution is towards the right. That's what I'm understanding here. Okay, let me check out the diagrams also. Okay, now it tells that it is positively skewed. Okay, positively skewed, what it told? Positively skewed, okay, indicates long tail on the right. Okay, so long tail on the right. This is the long tail on the right. Long tail on the right. I wrote left skewed. Just of understanding, as per understanding, I mentioned that if the more of the data distribution is towards the left, so it is left skewed. That's what I interpreted. However, however, the definition says that if we are having a long tail on the right, then it is right skewed. Okay, so if you go according to the definition, then change this thing. Then say it is right skewed. If more tail on the right, then right skewed. And if more tail on the left, then left skewed. Okay, so I'm making circles on what I have written. All right, fine. So there should not be any confusion. It's just a matter of interpretation. I wrote initially that this is left skewed. That means I interpret that more of the data is present on the left hand side. left oriented. However, the definition which is present in my notes, it says that if there is a long tail on the right, long tail on the right, then it is said to be right skewed. And this is this is positively skewed, positive skewness, and this is negative skewness. Okay, that means more tail on the left, more tail on the left. Okay, so it's just a matter of interpretation. How you think? I am referring that, okay, initially what I told, if I'm having a right orientation of the data, then it is right skew. That's what I said. But according to my notes, it's saying that no, it's saying that okay, kindly check out the tail. Then according to tail, you say if there is more tail on the right, more tail on the right, so right skewed. More tail on the left, left skewed. So right skewed according to them is positively skewed. Left skewed according to them is negatively skewed. So don't get confused. Okay, just how you interpret the things. I took the orientation. Okay, I took the orientation and they took the tail length. Okay, thank you for clarifying the direction of tail. Thank you, sir. So that's what you have to understand. Because most of the people get confused. There is a confusion. Okay, there is a big confusion. That's why sir has given the comment. The confusion is, sir, like we are seeing the data like this. So obviously it's looking like a left skewed because we are having the more orientation of the data on the left hand side. This is left side. So we say that okay, this is left skewed data. But what they mention in their definition, they mention that if you are having a long tail on the right, long tail on the right, so right skewed. Okay, but most of the people, okay, they see the distribution. That's why my initial statement was okay, this is left. My initial statement also was the same. I told that this is left skewed by seeing the orientation. There are two things which I interpret from my side. One is the orientation, one is the tail. Now, if you see the orientation, that means most of the data is present on the left. If you see the orientation, so most of the data is present on the left. So some people may say, okay, this is left skewed, but actually focus on tail. If there is long tail on the right, so right skewed. If there is more tail on the left, so left skewed. Now orientation, now again the thing, okay, this is right oriented, but okay, left skewed. Okay, it is left skewed because we are having a tail on the left, so left skewed. Left is negative, right is positive. That's it, finish. Now there should not be any confusion. Fine. Okay, now what else they are saying? Skewness defines the shape of the distribution. Okay, fine. So that's what we said initially, na? That's what we said initially, sir. Distribution is more on the left, sir. Distribution is present more on the left. So, sir, इसको left क्यों नहीं बोला आपने? इसको left skew क्यों नहीं बोला? Why you are not saying this thing as the left skewed? Because distribution, more of the concentration of the data is present on the left. Okay, but थोड़ा सा different. There is a different sense of understanding. All right, let me clear more things about it. We get asymmetry. Okay, the point is asymmetry in the data. Okay, we get asymmetry in the data. Okay, let me again get back here. We get a lot of asymmetry distribution, and these distributions are uneven spread of the data. There are two types of skewness, that means related to the spread of the data. Again, remember what it is focusing. Remember, spread of data. Okay, so positive means when the distribution takes so long tail. So skewness is referred to the tail. It is not referred to the concentration of the data. It is referring to the tail. If you are having a long tail on the right, so it is right skewed. Okay, that's what the people do have a problem. They do have a doubt. Sir, the data is looking to be left oriented. So it should be left skewed. No. If tail is more on the right, because we are referring skewness to tail. Okay, distribution of data means tail. So it is more on the right, right skewed. More on the left, left skewed. Okay, fine. So in the distribution, now here it is. This is right skewed. Now in the distribution, mean is greater than the median when we are having positive skewness. Okay, when there is a long tail on the right, it's saying that when there is long tail on the right, we are having positive skewness. Okay, and mean is greater than the median. See how this is positively skewed and mean is present here. Median is here, mode is here. Remember. So if mean is greater than the median, just in my yesterday's lecture, if mean is greater than the median, imputation is with the mean. Here there is no skewness. It's a normal distribution. This is your negatively skewed. Long tail on the left. So it is left skewed. So skewness is decided by the tail, in which direction it is, left or right. So this is negatively skewed. Long tail on the left. Fine. And here, here, mean is present at this side, median is present. This side, so obviously median is greater than the mean. Median, because median is present here, mean is present here. So median is greater than the mean. So imputation will be with respect to the mean here. Okay, fine. So that's what the basic understanding of the skewness. So I think, I hope, with this 15 to 20 minutes of lecture, now your concept related to the skewness is been cleared. So when I started, I told, okay, this is left skewed, this is right, just to make you aware that what the two kind of perception people have. Okay, the perception is related to the orientation, but we are not going to follow this. The perception should be related to the tail. That is skewness. All right, fine. Now next, what about your kurtosis? Again, it is same statistical measure. It describes the degree of peak or the flatness. It measures the shape of the distribution, especially the height and the sharpness of the central peak. Okay, so kurtosis, it's a Greek word, kurtos, which means curve. So it's trying to identify that how your data distribution, what they are having, sharp, or whether it is having a normal curve, or whether it is having a flat distribution. Okay, so how it looks. So kurtosis is useful to identify the outliers in the data. Distribution with high kurtosis will have more extreme values than the normal distribution. Let's see. We are having three types of kurtosis: mesokritic, leptokritic, and platykritic. Okay, so meso means in this type of distribution there is a symmetry. Means both extreme ends are similar. This is same as normal distribution. So mesokritic, normal distribution. Leptocritic means leptocritic means which is having longer tail. Indicates more significant percentage of data near the tail. This causes tail to be longer. Longer tails like this thing. It might be having a long tail. So on both the ends I am having long tails. This is leptocritic. And then platycritic. That means it is having low kurtosis than the mesocortic, shorter tail. Okay, that means few data is present on the tail, and we are having this makes the tail flatter. So this is first one is leptokurtic. Leptokurtic means longer tail. See here it is green one. This green one leptokurtic, long tail. Okay, mesocortic is normal distribution, blue one, normal distribution, and platycortic is like having short tail. Platycortic is short tail. Okay, it's not normal, but it is having more like flatness present. So that is platycortic. Okay, so again understand these points. Okay, we are checking the distribution of the data. Just remember this thing. So distribution, we check the skewness, how it is oriented according to the tail, and still also here we are focusing upon tail only. Okay, so it said that if you are having long tails on both sides, long tails on both sides. So the concept is mesocortic. Okay, long tails on. Okay, mesocortic symmetry. Sorry, long tails means leptocortic. Okay, more of the data is present near the tail when the tail is longer. So it is leptocortic. Okay, so there will be sharp turn like this. I think the diagram which I made initially should be corrected here. Okay, I was just focusing upon the tail. Okay, leptocritic. That means more of the data is on the tail, and there this will be sharpness, and here it is. More of the data will be present near the tail. This is leptocortic. Mesocortic is normal only. Mesocortic is normal distribution. This is meso. This is leptocritic. Okay, and leptocritic, mesocritic, and one more which we are having at the last, that is platycritic. In platycritic, we are not having so much long tail. We are just having tails like this, but we are having much more flatness here. This is platycritic. We are having flatness here in the data distribution. ये flat है. Okay, we are having more flatness here at the top. This is platycritic. Platycritic. Okay, so by seeing these, we are able to differentiate the data distribution from normal. This is normal. See, normal distribution is our reference plot, and according to our reference plot only, now we are defining the differences between what the actual is and how a normal looks like. Okay, you said someone skewed. You said that okay, this is skewed data. On what reference you said? Okay, on what reference you said? By comparing it with normal. Comparing it with normal. Because normal is having all mean median mode equal. Mean median mode all are equal in normal. But in case of skewed data, if you are having a long tail on the right, this is right skewed, where mean is greater than median. Okay, so obviously now where all are equal, then normal. When they are not equal, skewed. So here mean is greater than the median. For right skewed. For left skewed. Here median is greater than mean, because median is present here and mean is present here. And you can understand it's practical. See, mean will be shifted towards the tail. Mean shift towards tail. I already told you yesterday that why there is a skewness in the data. Why? Because presence of outliers in the data, in the data. That is the reason. There are certain points which are, big points which are present in the data distribution, and to plot them, okay, that's why the tail has been increased. That's the reason. So because of the presence of the outliers, you are getting the tails. And obviously, mean will be shifted because of the presence of outlier. It will be shifted in that direction only. So if the outliers are present more on the left hand side, so mean is less than the median. And if the outliers are present more on the right hand side, so mean will be greater than the median. So this is skewness. So this is right skewed, this is left skewed. And kurtosis, it told that flatness, peakness or flatness, peak or flat. So if you are having long tails, that means more data distribution is present here and less data is here. Okay, so it is leptokurtic. Okay, leptokurtic. And if less data is present on the tail, more data is present on the peak, then it is platykurtic. Platykurtic. Okay, this is platy. And if everything is like normal, then it is mesokurtic. So just remember, these are the basics of statistics. Okay, you have to remember this thing, and especially this skewness. Why? Because why skewness? Okay, why skewness? You have to remember because in our machine learning algorithms, they do demand they demand data to be normally distributed. So you have to check the distribution of the features. If they are not normally distributed, then you have to apply transformation. You have to apply transformation to convert them into normal distribution. And the transformations are like these are normalization or scaling processes. Okay, so for example, log. If there is a feature X that is not normally distributed, you can apply log to it. That means we try to change the orientation, like tailedness. No? We try to change the orientation of the data. You can apply log, you can take square root. Okay, these two are preferred, log and the square root. You try to convert them that it should look like normal. It's not mandatory that you would convert it perfectly normal, but you can try. But if the data is not normally distributed, and if you are directly using the algorithm, for example, if I say about linear regression, there is a demand of linear regression that numerical continuous features should have to be normally distributed. This is the requirement of linear regression. And if you apply normal this linear regression directly without doing the transformation, then it will give you wrong answer. It will give you more errors. बट इफ यू अप्लाई द algorithm, ये यही तो सीखना है हमें, हम इसलिए तो आए हैं यहाँ पे. We all are here for this purpose only, to understand the technique, what we can do over data, how we can understand the data, and what application we can do. That's what we are here to learn. Okay, so I will tell you the skills. Okay, check the orientation of the data. If it is not normally distributed, apply the transformation and then put that transformed data into the model for the training purpose. Okay, so important है ये बहुत ज़्यादा. And for this we are going to make histoplot. Okay, histoplot and distplot in data visualization. to check the skewness of the data. All right, fine, sure. So this is what we have to do. All right, let me get back to our notes. Fine. So positively skewed, I told mean greater than the median. Okay. So fine. Negatively skewed, mean is less than the median. Okay, we very well know. Okay, what about here related to the median? See, mean is greater than the median in positively skewed. Okay, and median is less than the mean and is closer to the first quartile. Technical. Okay, so median, that is Q2 actually. Median is Q2. Median represents 50% of the data. Yesterday only I taught this thing. So it's saying that in the positively skewed, Q1 and Q2 are closer, and Q3, it is at a far distance. Okay, fine. All right. Then in case of negatively skewness, negatively skewness, mean is less than the median. Just I have shown you over the plots. You know about this thing. And median, which is greater than the mean, is closer to the Q3, third quartile. That means Q1 is here, Q2 and Q3 are closer. Acha, yes, yeah, self understood. This is self understood. If I don't tell you, na, that then also you should interpret by seeing the distribution of the data. Okay, fine. And what about the mode in case of negatively skewness? Mode is more than median and the mean. While in case of positive skewness, mode is lower than median and the mean. So technically, you should remember these points. Which is greater, which is smaller, what is skewness, what is kurtosis. Okay, so that's what you have to remember. Very technical points. And by seeing the figure also, okay, we understood. Fine. So skewness, skewed distribution, the mean is more sensitive to extreme values. Tail. Median is less affected by outliers. Yesterday only I told. Okay, whether it is right skewed or left skewed, you can see in the diagram. Okay, you can see in the diagram. Okay, see here. If it is right skewed, median is here. If it is left skewed, then also median is here. So median is less impacted by the skewness. The one which is impacted is mean. ये लफड़ा मीन का है, मीडियन का नहीं. Okay, so that's why I told yesterday also. If you want to perform imputation, if you want to fill empty value, just check the orientation of the data, check the distribution of the data, draw the plots, and see how the data distribution is. Then accordingly, fill the data value with those either median or mean. Preferred is mean. We do prefer mean. All right, but do take care of the distribution of the data. All right, and then you can decide from that side. All right, fine. Now, so these are the points. Okay, it's mentioned, so I cleared. Fine. Then frequency distribution. Frequency is the measure of occurrence of an event in a data set. How many times a data value occurred, that is the frequency. Measures of dispersion, that means how data is spread in the dimension. Measure of see, there is measure of central tendency, and we are having measure of dispersion. Measure of dispersion means how spread data is. Again, this is also important. IMP. Here we are having range, variance, standard deviation. Okay, so range means interval, max and the min value. So for example, this. Okay, so minimum is 12, maximum is 100, range is 88. 100 minus 12, 88. So the data is distributed between 12 and 100. Variance, variance means, okay, difference between each value of the data from its mean. IMP, mark karo sir, IMP, important. That means x minus x bar, that is variance. Variance, it means how far a data point is from its mean, that is called as variance. And don't forget this definition. Variance means how far a data point from its mean. Okay, so this is the distribution of the data. If you want to find the variance of this, okay, if this is the mean, calculate the distance. If you want to find the variance of this point, calculate the distance. This point, calculate distance. This point, calculate distance. This point, calculate distance. This tells the variance. Difference of a data point from its mean. Okay. This is sample variance. Actually, now you are having two things. One is population data, one is sample data. Sample you take from population only. This is population. This is sample. You pick it. So we are having sample mean also. We are having population mean also. This is sample mean. If you write x bar is sample mean, and this is sample variance. Okay, and they have mentioned x minus x bar ka whole square ka summation divided by n minus 1. N minus 1, these are the data points. N is the data points, number of data points. So don't get confused. See, don't get confused. This is how they are writing the formula. Now, in general context, remember, in a general, distance of a point from its mean is called variance. If it calculate all x minus x bar, it will do the square, so that distance should not be root. रूट वाला कॉम्प्लेक्स हो जाएगा, कोई डिस्टेंस तो रूट में, तो ये होता है x माइनस एक्स बार डिवाइडेड बाई n माइनस वन, दैट इज n इज द नंबर ऑफ डेटा पॉइंट्स. तो ये हो जाएगा सैंपल वेरिएंस. ये सैंपल का वेरिएंस. लेट्स टेक all the data points and calculate the difference from the mean. Square them. Sum square. Okay. That means if you are having x1, x2, x3, and the mean is x bar of x1, x2, x3. So it will be like x1 minus x bar ka square plus x2 minus x bar ka square plus x3 minus x bar ka square divided by n minus 1, yani 3 minus 1, yani 2. So this is sample variance. And we are having population variance also, and the difference is just only in case of population variance you use new. Remember, ye bhi technical hai. If you see x bar, this is sample mean, this is sample mean. And if you take new, this is population mean. ये terms का भी technical meaning है. This is population mean. So sample mean, population mean. So if you want to calculate the variance of population, it will be x minus nu upon n. तो ऐसा कर दो इसको, स्क्वायर का समीशन. दिस इज पॉपुलेशन वेरिएंस. Population variance. Okay, let me show you here. Okay, so this is population variance, where capital N, again the number of data points, and standard deviation is the square root of variance. Okay, that is the square root of variance. If I take the root, if I take the root of sample variance, so that will be standard deviation of the sample. And if I take the root of standard of the population, so that will be for the standard deviation for the population. Okay, so we are having two things. Okay, your sample and population. In general we do work upon sample. Okay, in general we do work upon sample. Okay, applying probability and all these things. Sample, we do take the sample. Okay, but you should be understanding, if x bar written, sample mean. If new written, population mean. Population is the entire data. Sample is a portion of a data, subset of that data. Okay, that's what you have to understand. Okay, fine. Then you are having covariance. Covariance is to compare the variance of two numerical variables. Okay, two numerical variables. So for example, you are having two variables, x1, x2. Okay, and these are the entries of x1. These are the entries of x2. Just take the mean of x1. All the data points. Just take the mean of x1. All the data points. Okay, fine. That is, let us suppose let us suppose this is x1 bar, and take the mean of all x2 values. This is x2 bar. So x minus x1 bar, yani every data point of x1 minus its mean, product every data point of x2 minus x2 mean. Take the summation, mark them I. Okay, I. So this is x1i, this is x2i. That means take every data point, take this thing, put it here, take this thing, put it here, plus take this thing, put it here, take this thing, put it here, plus this thing, this thing, plus. So that's the summation means, divided by n. This is called as covariance. So covariance, that means between two variables. Okay, previously it was like x minus x bar ka whole square. Now instead of square na, you are just multiplying two things, multiplication of two things. You are not taking the whole square. Okay, fine. So this is called as covariance. We are having more things to study about the covariance. Okay, it's just a starting. All right, I hope you understand. So x and y represents two variables. N is the number of population, yeah, number of data points. So this is how we represent covariance. We are having Pearson correlation, or the Pearson correlation. Okay, where we do write covariance. Okay, so covariance of x comma y, that means covariance between x and y. That means the above formula which you have used right now, divided by standard deviation of x and standard deviation of y. So this is standard deviation of x, that means square root of the variance of x, and this is the square root of the variance of y. That's it. This is Pearson correlation. And it is very much important. IMP, again, let me mark this thing important. Correlation. It is telling correlation between variables, how variables are correlated. And why I'm saying that it is important, because it put impact on your model. Okay, it put impact on your model. For example, this is your data. This is x1, x2, x3, y. Y is your target. If x1 and x2 are highly correlated, that means if I change x1, x2 is also changing. That means they are highly correlated. So, in general, according to the rules for the model development, it tells that we are not going to keep correlated features, because they will lead to overfitting in the data. हमको correlated feature नहीं रखना है. We do not have to keep the correlated features in a model for the training, because one is increasing, another is also increasing. That means model, if it is able to capture point of x1, it will also able to capture the point of x2, and model will say yes boss, भाई मेरे को तो सब समझ में आ रहा. The model will say that I am able to understand everything. If the model can capture point of x1, model can capture point of x2 also. Model will become confident, and model will say yes, I am able to understand everything. But actually में क्या हुआ, वो तो correlated थे भाई. Okay, correlated थे. That means the data points of x1 and data point of x2 are like they might be in a line. Okay, So model, if it is trying to capture x1, it will able to capture x2 also, उसको मिल गया. लेकिन what I want from the model is to do effort. I want the model is to do the effort. Okay, that's what I want. But instead of doing the effort, the model captured one feature data point, it automatically captured another feature data point because both are correlated. So ये मैं नहीं चाहता. So इसीलिए for that reason only we are having correlation. Okay, we should identify the correlation. So there is a value for correlation -1 to +1. -1 means negative correlation. +1 means positive correlation. Okay, and in between there is zero. That means no correlation. So what we expect is there should be least correlation between the features. Okay, negative correlation also means highly correlated. That means if one is increasing, another is decreasing at the same rate. Negative का मतलब ये होता है. Positive correlation means if one is increasing, another is increasing with the same rate. ये positive होता है. Negative means if one is increasing, another is decreasing at the same rate. तो मेरे को -1 and +1, I don't want these two types of the correlation values. If it is like 0.001, I am happy. If it is zero point 0.1, I am happy. But if we are having a correlation more than like this 0.78, ये बहुत ज्यादा correlation है. Or if I am having -0.78, this is also highly correlation. It means that if x1 is increasing, x2 is decreasing with a rate of 78%. Okay, so this is also high correlation, but in a negative direction. Negative means direction. That means one is increasing, another decreasing. That means this is inverse. This is inverse, and this is directly proportional. So x1 is directly proportional to x2. It means this. X1 is inversely proportional to x2. This means okay. So I need to take care of the correlation. Very much important. So here now we had Pearson correlation, and this is the formula for Pearson correlation. That means kindly calculate the covariance divided by the standard deviation of x, standard deviation of y. Okay, these two multiplication, and here is the formula, and that's what I told now. -1 to +1. The value fluctuate between -1 to +1. -1 means negative relationship. +1 means positive relationship. 0 means no relationship. I am happy. Okay. 0 means no relationship, so you will be happy with that. Okay, fine. So this is Pearson correlation. All right. So that's all the things which are mentioned here. R is the degree of association. Okay, +1 means strong positive correlation. -1 means strong negative correlation. Close to 0 means no correlation. Okay, fine. So that's it. That's related to the Pearson correlation. We'll explore more about it, but not today. Okay. So yeah, it means yeah. I got some comment here. Please answer the following: do decision trees, random forest system, gradient boosting trees assumptions about the distribution feature? Sir, actually, now in SVM, in SVM, we have to take care of the distribution, and actually SVM is a distance based algorithm. So here we do scale our data, and we do perform standard scaler. This kind of operation in pre-processing we apply with SVM. But decision tree, random forests, sir, they don't say. in regards to distribution. They don't say that we require scaled data or normalized data, or it should be normally distributed. No. Decision tree, random forest, gradient boosting, they don't say that we want. Their concern is related to the outliers, so especially outlier and feature independence. That, like just right now which I told, there should not be any correlation or least correlation, and there should not be any outliers in the data. That's what the decision tree, random forest, and gradient boosting they say. Okay, they don't like specifically tell ki the data should be like normally distributed. No, they will not say. If the features are highly correlated, sir, that is issue for each and every algorithm. Each and every algorithm says that we require least correlated data, least, और ना हो तो वो तो बहुत अच्छी बात है. We want least. This is common for all. Outlier removal, common for all. Least correlation, common for all. But what is not common is, for example, normally distributed linear regression demand, not decision tree, not random forest. Scaling of the data, support vector machine demand, not decision tree, not random forest. Yes, all the models require normal distribution in linear regression, and linear regression and lasso and ridge regression. That means which are the associates of linear. They demand. However, it's clearly mentioned in linear, especially. But let's include lasso and ridge also. All right. So these are the fundamentals. Fine. All right. Let me